So to finish up chapter 3, this last section, 3.3, deals with systems with 3 variables. So what we're going to find is that we're going to extend our conversation about systems of equations to larger systems. You're going to have 3 equations with 3 variables, and in fact, you could really do this for any size system. So you could have 15 equations and 15 variables. Typically, the number of equations and the number of variables needs to match in order to have a high likelihood of getting a solution. There are times where you don't have to have that, but typically that's going to be the preferred scenario. Okay. Now with more than 2 variables, so here you got x, y, and z. You start to expand that, and you use more letters, or you may use letters and subscripts if you get like 100 variables out there. We're not going to deal with anything that big. We're going to stick with 3 equations, 3 variables, typically x, y, and z as the variables. Now, if you think about with the 2 variable systems, they represented lines, and the solutions were the intersection of the lines. Well, with 3 variables, you have to extend that into 3 dimensions, right? So 2 variables are 2 dimensions, x, y. Now we go to a 3rd dimension. And so what we're actually looking at, each of these equations doesn't represent a line, it represents a plane, okay, like a sheet of paper, but stretched out infinitely far. And so the solution is again going to be a point of intersection of 3 planes, okay? So you maybe be able to visualize that. It's kind of like the corner of a room, right? You have a wall and a wall and a floor. That's 3 planes. The corner is the point of intersection of those 3 planes, okay? You don't need to know a lot of the details of that. You don't need to graph these. We're not looking for that. We're just looking for the solution, what the coordinates of that point are. And the coordinates of that point are found, again, using either substitution or addition method. Typically, the substitution method with these is very hard because you're going to be substituting multiple times. The equations get really long when you start putting in all the parentheses because there's so many variables involved. Typically, the addition method is the quickest way to eliminate variables and get this down to a workable equation. The end goal here is to try and eliminate some variables. So if I've started with 3 variables, what I really want to do is get it down to 2 and then get it down to 1. So just kind of like scaling it down to an equation with 1 variable, solve for that variable, and then gradually substitute back to find the other ones, okay? So if you think about this, I look at my 3 variables and I want to eliminate one of them. So the question is, which variable is easiest to eliminate? And I'm just looking at the coefficients here. Any of them will work. In fact, it may not be that bad. I might choose the z in this case because I've got a couple z's with coefficient of 1, and so, well, -1. And so it might be easy to get those to match up to the 3 and make this work out. The difficult part in starting this is that you can't use all 3 equations at one time. Well, you could, I suppose, but it often makes it more complicated. I think the best approach is to select 2 of the 3, and it doesn't matter which 2. You can take the top 2, the bottom 2, or the top and bottom. Doesn't matter. You take 2 of them, eliminate a variable, then you take a different pair. Okay, so you can do top 2 and then bottom 2. You can repeat an equation, but you can't repeat them both. So you take 2, eliminate a variable, take 2 more, eliminate the same variable, and what you'll have is a resulting 2 equations that only have 2 variables because you've eliminated 1. Okay, and then you proceed like we did in previous sections. That's just an overview. We'll go through and give you a concrete example of how that works. So let's focus on the variable z for a moment, and let's try to eliminate that. In this case, I'm going to just take the top 2 equations. To get the z's to be opposite, I have one at +3, I have one at -1. I want to get the -1 to be a -3. So I'm going to multiply that equation by positive 3. I'm going to distribute the positive 3 to all of the terms. Remember, when we multiply both sides of the equation, it distributes to every term. So this equation will become 3x plus 6y minus 3z equal to 0, right? 3 times 0 is 0. So that's 3 times everything. The top equation is just going to stay as is. Okay, so that one I'll just bring over and call it 2x minus 4y plus 3z equals 17. And when I add those together, term by term, I get 5x plus 2y, the z's are gone, equals 17. Okay? So now I have an equation that has two variables. I've eliminated one variable. The problem is, in order to solve an equation with two variables, I actually need a second one. And to do that, I'm going to mix two of the other, or a different combination of these three equations. So instead of the top two, I need to choose a different pair. It doesn't matter which other pair, either the top and bottom or the bottom two. I'm just going to take the bottom two, maybe. Again, it won't matter. I'll take those two, switch my color. And what I want to do is get the z's, and again, it has to be the same variable that I eliminate. So if I eliminate a z here, I've got to eliminate it again here. I'm going to try to get the z's to have an opposite coefficient. In this case, a positive one and a negative one would be the best. So I'm going to take the, let's take the top equation, multiply it by a -1. And then I'll just I'm going to keep this bottom equation here. I'm just trying to think how I want to structure this on the board. I'm going to keep my bottom equation, and I'm going to take this middle equation and multiply by a -1. Okay, that's going to change my sign on the z so they add up to 0. But to do that, I got to distribute it to every term. So I get -1 times x is -x. -1 times 2y is -2y. -1 times -z is positive z or plus z. And -1 times 0 is, of course, 0. Okay. Now I can add these two equations together. Again, it's a combination that's different from the original two that I chose. And when I add these two together, 4x minus x is 3x. -y minus 2y is -3y. The z's drop out. And on the other side, I get 6 plus 0 is 6. So now I have a system of two equations with two variables, x and y. I'm going to bring them together to form a new system that I then have to solve. So it's a sort of a scaling process. You start with a large system, bring it down to a smaller system, and then solve at the end. So I'm going to take 5x plus, actually, you know what? I don't need necessarily to rewrite this. What I want to do, I could rewrite it as a new system, kind of like we do here with this, with the brace and everything, but I'm going to just take the two equations, try to figure out what I need as my opposite coefficients, and then just multiply them as I bring them down so I can take care of a couple steps here. This one has a 3x and a -3y, 5x and 2y. I'm going to go ahead and get rid of the y's because they already have opposite signs, so it's one less thing to worry about is changing the sign. To do that, I need to multiply the blue equation by 3 and the green equation by 2, and that will get them both to the least common multiple of 6. Let me write this up. So the blue equation, I'm going to multiply by 3, and that will give me 15x plus 6y equals, what's 3 times 17 is 50, 51. I should know that faster. And then the green equation I want to multiply by 2. Times by 2. So I'm going to get 6x minus 6y equals 12. Okay. Then I can add those two equations together using the addition method again. The y's drop off nicely. I get 21x. And 51 and 12 make 63. And when I divide out the 21, well, 63 divided by 21 is 3. It works out nicely, so x is 3. Once I have a single variable solved for, I want to take that value and substitute it back into the equations gradually to find the other two values, right, the y and the z. Because I started here in this last step with the x and y, I want to substitute it back in to find y first. Now I could use either of the two equations I just used in the last system. It won't matter. I'm going to go ahead and use this top one. Again, it doesn't really matter. I just see fewer negatives and stuff to deal with. So I'm going to use that. So I'm going to take 5x, or 5 times x, which would be 3, right? So 5 times 3 plus 2y equals 17. Now darken that 3 up. And so now I solve that. We're going to have, 15 plus 2y equals 17. If I subtract the 15 from both sides, I'm going to have a 2 on the other side. So I'll have 2y is equal to 2 after subtracting. And then dividing out the 2, obviously I'm going to get a 1 for the y. So y is equal to 1. I'm not going to show all the details of those steps, but that should be clear there. And so then I'm going to take that value, that y value of 1, and along with the x value of 3, so I've got x and y, and I'm going to replace them back into one of the 3 original equations to find z. Now, just like with systems of 2 equations, it won't matter which one I put it in. I'll get the same value of z for each of the 3 equations. So I just picked the one that I think the arithmetic will work out nicest on. Let's do the middle one. The numbers are all kind of smaller there, right? So let's do that. So my x value, I'm going to start with x plus 2y minus z equals 0. That's the structure of the equation. Then I have to substitute in the x value of 3 and the y value of 1. And then I go through and solve for z. So 3 plus 2 times 1 is 2. 3 plus 2 is 5, so I get 5 minus z equals 0. And a quick way to finish this off is to add the z to both sides. And so we're going to get 5 equal to z. So 5 is the value for z in the end. So now I'm looking at this, I've got a solution. I've got a solution or a number for each of the 3 variables. But remember, we need a point. And we talked about an ordered pair to solve systems with 2 equations. Now we're going to talk about an ordered triple. We need 3 values in the x, y, z combination. We typically go alphabetical on those. Okay, so the solution set is again a set containing a point, but this time the point is an ordered triple. If you think about it in a 3-dimensional space, it's a point that has an x, a y, and a z. So you've got all 3, I should say x, y, and z, something like that. You get all 3 values together, So we would have 3, comma, 1, comma, 5 should be the solution to this system. And now as just a quick check, just to make sure that works, I'm going to take 3, 1, and 5 and plug them back in my mind. I'll do it in my mind, but I'll speak it out to you rather than writing it down. And just make sure everything adds up right. So 3, 1, and 5, if I put them in the first equation here, 2 times 1 is 2. I'm sorry, did that wrong. 2 times 3, right? 3. 3 in for x. So 2 times 3 is 6. 4 times 1 is 4. 3 times 5 is 15. 6 minus 4 is 2. Add the 15, you get 17. So that works out. I do 3, 1, and 5 again. 3 plus, this will be 2. 3 plus 2 is 5. Minus the 5 for the z would make 0. 5 minus 5 is 0. That's what we have here. This one, I do 4 times 3, which is 12. Minus 1 is 11. Minus 5. 11 minus 5 is 6. That's what we have here. So it works. This point works to make all 3 equations true. Okay? All 3 equations have the same amount on both sides.